Hello everyone, welcome back to ECE100, class number 11. In this class we're gonna solve some little bit complex circuits, and we're gonna use equivalent resistance technique both for series and parallel, and to solve a little bit of complicated circuit, to help you out how to solve circuit in electrical and computer engineering. So if you look at this one here, this is one of the amplifier, 100-watt amplifier circuit. You can see that there's a lot of different components here. You can see there are transistors, there are diode. Transistors are right here. And you might see a diode somewhere right here. There are diode here. And there are also capacitors right here. And there are a lot of resistors here and there. So they're not in straightforward series or parallel connection. They're a combination of both. So how to solve this kind of circuits? You will learn this kind of circuit more in your junior year, but let's start from the small complicated circuit. Before we do the here, go to complex circuit, let's discuss a topic called nodes. What are the nodes? Nodes are basically a connection point in your circuit where two or more circuit component connect together, and also has the voltage at the node same value. That means if you look at here, here two circuit component like voltage source and the component there connected together. Here's another one here, and here's another one here, and here's another one here. So there are these are the four nodes for this circuit. Each of the nodes. So if I say this one is V1, this one is V2, this one is V3, this one is V4. That means at this node, particular these nodes over here, if I say this voltage is V2, that means this node has voltage which is V2, all right? So it's the same value for all the component connecting to the node. So that's the node over here. So with that, if you look at this one here, how many nodes you can see over here? Think about it. For example, this is one node over here. And also this, look at here, this is the whole thing together. It's one node over here. There's another node over here, right? Then if you look at here, this is the reference point. We call it 0 volts, and also it's 0 volts here. That means these two have the same voltage. If they're not, even though they're not physically connected in the circuit, but they have the same voltage. So that means that, so this whole thing is basically one node here. So that's how it is. I mean, node has its connection points in the circuit who have the same voltage. That means in a node, in a circuit, you have a common ground. So that common ground is a single node for the whole circuit. So let's look at the circuit over here. So in your circuit, as you see over here, it's not a straightforward series or parallel circuit. I would say it's a combination of both. So how do you solve it? To solve it, first you have to make sure that what resistors are connected in series, what are connected in parallel, and how do you go from one end to another end. So over here, if I define the nodes over here, so I can see that there's one node over here, right? And another node over here. So if I say this one is V1 voltage, this is V2 voltage. So the difference between these two nodes is V1 minus V2. And you can see that that difference of voltage come across this both 100 ohm resistor. That means these 100 ohm resistors, both of them are across the same voltage. That means they share the same voltage. When elements shares the same voltage, they're in parallel connection. That means these 100 ohm and 100 ohms, they're in parallel connection. So start from there, and then we'll go ahead and see how circuit look like. So to do that, so I know that these two are in parallel connection here. So we'll make one out of these two. So let's draw that. So this one over here, this resistance over here, I know this is the 200 ohm, and this is 25 ohm here. And now this is a combination of these two. So 100 and 100, if we combine them in parallel. So let's see what that's look like. So let's say is R equivalent prime, for example. That would be 1 over, let's say this is R1, this is R2, for example. So R1 over R2. If you do the math here, so equivalent prime would be your 50 ohms. All right, that means this is your 50 ohms now. So this circuit becomes that circuit now. So now if you look at that, if you now have a current over here in the circuit, all three resistors will have the same current. That means they're in series. So your final R EQ would be, this all series here, say 275 ohms. So that's how you solve a little bit of complicated circuit with series and parallel combinations. For this one here, if you apply the same logic, so find out where you have the parallel connection first, then and reduce them, then go one by one. So if you look at here, if you look at these two, they're in parallel connection because they have the same voltage across them. And also, if you look at these two here, they're also in parallel connection. They also have the same voltage across them. So if I now reduce this connection over here, so that's what look like here. So this is your 1 ohms right here. This is the parallel combination of 10 and 40. This is 60. I'm gonna put it over here. And this is a parallel combination of 250. This is 5 ohms over here. So now, if you use the equations I gave you in the last circuit, the 10 and 40 will give you 8 ohms here. And 50 and 200 will give you 40 ohms here. You can check with your equations. Now look at that, if I put a current here, all of them will share the same current. That means all of them are in series. So that means your R equivalent over here would be, if you add all of them, you should get 114 ohms. So that's how you solve the very complicated circuit. So now let's see how do you use all this together. So when you try to solve a circuit, first you try to do how to basically use a technique to solve the circuit here. So to do that, we try to solve a circuit like this. So try to make sure that you know the current direction first. To assume a current direction, we assume the current direction is this way here. Based on the current direction, we now assign the polarity to the resistor. So in the resistive circuit, source is here. In the source, current goes from negative to positive. In the resistance, current goes from higher potential to lower potential. So this is the higher, this is the lower potential here. This is the higher, this is the lower potential here. Again, this is the higher, this is the lower potential. Depending on current. So in the load, current goes from higher potential to lower potential. This is the your circuit assumption to solve the circuit. So now let's say the voltage across is V1, voltage across this one is V2, voltage across this one is V3, right? So this is how you assign the polarity to the load depending on your current direction. If you reverse the current direction, that will go in the reverse direction. All right? So now I did for this one here, again, it's positive, negative, positive, negative, positive, negative. Let's say this is V1, this is V2, this is V3 here. So now, if I try to find the current here, R equivalent for this circuit, if you look at that, all the resistance has the same current. So R equivalent would be, for you here is 70 ohms, right? Then your I would be your 10 volts over 70 ohms. That will give you 143 milliamps, right? That's the current here. So now use the current. Now you can find each of the V1, V2, and V3 here. So V1 would be I, the current you have, times R1. Let's say this is your R1, this is your R2, this is your R3. And if you do the math over here, you know current 143 milliamps and your R1 is 50, so you'll get 7.1 volts for that one, and V2 you'll get 0. Let's see what is the value here, 143 times 5, so 0.1343 times 5 will give you 0.71, so 0.1343 0.715 volts, and V3 would be your 2.14 volts, right? So those are the voltages across each of the resistor. We call them voltage drop because you're going from positively higher potential to lower potential. So we call them voltage drops. So V1, V2, V3, those are all voltage drop across the respective resistors. So we found them. So your V1, V2, V3, you all found them. So now if we add them together, so V1 plus V2 plus V3, if we add them together, as you found them, what they were 7.14 volts plus 0.715 volts plus 2.114 volts. If you add them together, you will see that you'll get 9.999 volts, right? So that is basically very close to your source voltage. So Vs is basically supply voltage Vs, which is 10 volts, is equal to V1 plus V2 plus V3, which is called that your voltage drops are equal to voltage rise. When the voltage goes from negative to positive, right here is called rise. So voltage drops in the circuit equal to voltage rises. That's what it's saying. Oops. So voltage drop, it should be equal to voltage rises in a circuit in a loop. All right. So now I'm going to define. This is called a loop here. I'm going to define the loop now. What is a loop? So loops, a loop, you have a starting point in the circuit and will go around and travel the circuit path and come back to the same starting point again without passing a node more than one. So let's say if I have, if I start from here for this one, I can go across this and come back to this point. So in that, I did not pass any nodes. So there's a node over here, 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 right? So I can come back to the same point, but I did not pass any node twice. I can do the same thing over here, like come back to the same point over here. So I did not pass any node twice. And also I can do one more here, go back and come back here. So there are three of them, right? I can potentially make three loops here in this circuit without passing a node more than once. So there are three loops here. And you also notice that a loop can also have another loop inside it. So there's a loop over here, this loop over here. This loop has the other loops inside that. Loop can contain another loop inside it as long as you are not passing a particular node more than once. So there's the loops. If you look at here, how many loops here, we're going to ask you in the class, see can you find how many loops in this circuit. All right. That's all for today, and we'll see you in next class.